Multiple processor scheduling. If multiple CPUs are available, load sharing becomes possible, but scheduling problems become correspondingly more complex. Many possibilities have been tried, and as we saw with single processor CPU scheduling, there is no one best solution. We concentrate on systems in which the processors are identical, homogeneous in terms of their functionality. We can then use any available processor to run any process in the queue. Even with homogeneous multiprocessors, there are some limitations on scheduling. Consider a system with an input-output device attached to a private bus of one processor. Processors that wish to use that device must be scheduled to run on that processor. Approaches to multiple processor scheduling. One approach to CPU scheduling in a multiprocessor system has all scheduling decisions, input-output processing, and other system activities handled by a single processor, the master server. The other processors execute only user code. This asymmetric multiprocessing is simple because only one processor accesses the system data structures, reducing the need for data sharing. A second approach uses symmetric multiprocessing, SMP, where each processor is self-scheduling. All processors may be in a common ready queue, or each processor may have its own private queue of ready processors. Regardless, scheduling proceeds by having the scheduler for each processor examine the ready queue and select a process to execute. If we have multiple processors trying to access and update a common data structure, the scheduler must be programmed carefully. We must ensure that two separate processes do not choose to schedule the same process and that processes are not lost from the queue. Virtually all modern operating systems support SMP, including Windows, Linux, and Mac OS. pthread Scheduling API. Processor affinity. Consider what happens to cache memory when a process has been running on a specific processor. The data most recently accessed by the process populate the cache for the processor. As a result, successive memory accesses by the process are often satisfied in cache memory. Now consider what happens if the process migrates to another processor. The contents of the cache memory must be invalidated for the first processor, and the cache for the second processor must be repopulated because of the high cost of invalidating and repopulating caches. Most SMP systems try to avoid migration of processes from one processor to another and instead attempt to keep a process running on the same processor. This is known as processor affinity, that is, a process has an affinity for the processor on which it is currently running. Processor affinity takes several forms. When an operating system has a policy of attempting to keep a process running on the same processor, but not guaranteeing that it will do so, we have a situation known as soft affinity. Here, the operating system will attempt to keep a process on a single processor, but is possible for a process to migrate between processes. In contrast, some systems provide system calls that support hard affinity, thereby allowing a process to specify a subset of processes on which it may run. Many systems provide both soft and hard affinity. For example, Linux implements soft affinity, but it also provides the SCHED set affinity function system call, which supports hard affinity. The main memory architecture of a system can affect processor affinity issues. Figure illustrates an architecture featuring non-uniform memory access (NUMA), in which a CPU has faster access to some parts of main memory than to other parts. NUMA and CPU scheduling. Typically, This occurs in systems containing combined CPU and memory boards. The CPUs on a board can access the memory on that board faster than they can access memory on other boards in the system. If the operating system CPU scheduler and memory placement algorithms work together, then a process that is assigned affinity to a particular CPU can be allocated memory on the board where the CPU resides. This example also shows that operating systems are frequently not as cleanly defined and implemented as described in operating system textbooks. Rather, the solid lines between sections of an operating system are frequently only dotted lines, with algorithms creating connections in ways aimed at optimizing performance and reliability. Load balancing. On SMP systems, it is important to keep the workload balanced among all processes to fully utilize the benefits of having more than one processor. Otherwise, one or more processes may sit idle while other processes have high workloads along with lists of processes awaiting the CPU. Load balancing attempts to keep the workload evenly distributed across all processes in an SMP system. It is important to note that load balancing is typically necessary only on systems where each processor has its own private queue of eligible processes to execute. On systems with a common run queue, load balancing is often unnecessary because once a processor becomes idle, it immediately extracts a runnable process from the common run queue. It is also important to note, however, that in most contemporary operating systems supporting SMP, each processor does have a private queue of eligible processes. There are two general approaches to load balancing: push migration and pull migration. With push migration, a specific task periodically checks the load on each processor and, if it finds an imbalance, evenly distributes the load by moving or pushing processes from overloaded to idle or less busy processes. Pull migration occurs when an idle processor pulls a waiting task from a busy processor. Push and pull migration need not be mutually exclusive and are, in fact, often implemented in parallel on load balancing systems. For example, the Linux scheduler and the ULE scheduler available for free BSD systems implement both techniques. The benefit of keeping a process running on the same processor is that the process can take advantage of its data being in that processor's cache memory. Either pulling or pushing a process from one processor to another removes this benefit. As is often the case in system engineering, there is no absolute rule concerning what policy is best. Thus, in some systems, an idle processor always pulls a process from a non-idle processor. In other systems, processes are moved only if the imbalance exceeds a certain threshold. Multi-core processors. Traditionally, SMP systems have allowed several threads to run concurrently by providing multiple physical processors. However, a recent practice in computer hardware has been to place multiple processor cores on the same physical chip, resulting in a multi-core processor. Each core maintains its architectural state and thus appears to the operating system to be a separate physical processor. SMP systems that use multi-core processors are faster and consume less power than systems in which each processor has its own physical chip. Multi-core processors may complicate scheduling issues. Let's consider how this can happen. Researchers have discovered that when a processor accesses memory, it spends a significant amount of time waiting for the data to become available. This situation, known as a memory stall, may occur for various reasons, such as a cache miss, accessing data that are not in a cache memory. Figure below illustrates a memory stall. In this scenario, the processor can spend up to 50% of its time waiting for data to become available from memory. To remedy the situation, many recent hardware designs have implemented multi-threaded processor cores in which two or more hardware threads are assigned to each core. That way, if one thread stalls while waiting for memory, the core can switch to another thread. Figure below illustrates a dual-threaded processor core on which the execution of thread 0 and the execution of thread 1 are interleaved. From an operating system perspective, each hardware thread appears as a logical processor that is available to run a software thread. Thus, on a dual-threaded, dual-core system, 4 logical processors are presented to the operating system. The UltraSPARC T3 CPU has 16 cores per chip and 8 hardware threads per core. From the perspective of the operating system, there appear to be 120 logical processors. In general, there are 2 ways to multi-thread a processing core: coarse-grained multithreading, fine-grained multithreading. With coarse-grained multithreading, a thread executes on a processor until a long latency event such as a memory stall occurs. Because of the delay caused by the long latency event, the processor must switch to another thread to begin execution. However, the cost of switching between threads is high since the instruction pipeline must be flushed before the other thread can begin execution on the processor core. Once this new thread begins execution, it begins filling the pipeline with its instructions. Fine-grained or interleaved multithreading switches between threads at a much finer level of granularity, typically at the boundary of an instruction cycle. However, the architectural design of fine-grained systems includes logic for threading switching. As a result, the cost of switching between threads is small. Notice that a multi-threaded multi-core processor actually requires 2 different levels of scheduling. On one level are the scheduling decisions that must be made by the operating system as it chooses which software thread to run on each hardware thread, logical processor. For this level of scheduling, the operating system may choose any scheduling algorithm. A second level of scheduling specifies how each core decides which hardware thread to run. There are several strategies to adopt in this situation. The UltraSPARC T3, mentioned earlier, uses a simple round-robin algorithm to schedule the 8 hardware threads to each core. Another example, the Intel Itanium, is a dual-core processor with 2 hardware-managed threads per core. Assigned to each hardware thread is a dynamic urgency value ranging from 0 to 7, with 0 representing the lowest urgency and 7 the highest. The Itanium identifies 5 different events that may trigger a thread switch. When one of these events occurs, the thread switching logic compares the urgency of the 2 threads and selects the thread with the highest urgency value to execute on the processor core. Operations on processes. The processes in most systems can execute concurrently, and they may be created and deleted dynamically. Thus, these systems must provide a mechanism for process creation and termination. Process creation. During the course of execution, a process may create several new processes. The creating process is called a parent process, and the new processes are called the children of that process. Each of these new processes may in turn create other processes, forming a tree of processes. Most operating systems, including Unix, Linux, and Windows, identify processes according to a unique processor identifier, or PID, which is typically an integer number. The PID provides a unique value for each process in the system, and it can be used as an index to access various attributes of a process within the kernel. A typical process tree for the Linux operating system is shown below. It is easy to construct a process tree similar to the one shown in above diagram by recursively tracing parent processes all the way to the init process. Explanation of the above tree. In the init process, which always has a PID of 1, serves as the root parent process for all user processes. Once the system has booted, the init process can also create various user processes such as a web or a print server, an SSH server, and the like. In the above figure, we see two children of init, kthread and sshd. The kthread process is responsible for creating additional processes that perform tasks on behalf of the kernel, in this situation, kelper and pdflush. The sshd process is responsible for managing clients that connect to the system by using SSH, which is short for Secure Shell. The login process is responsible for managing clients that directly log onto the system. In this example, a client has logged on and is using the bash shell which has been assigned PID 8416. Using the bash command line interface, this user has created the process PS as well as the Emacs editor. On Unix and Linux systems, we can obtain a listing of processes by using the PS command, for example, PSEL. The command will list complete information for all processes currently active in the system. In general, when a process creates a child process, that child process will need certain resources: CPU time, memory, files, input-output devices to accomplish its task. A child process may be able to obtain its resources directly from the operating system, or it may be constrained to a subset of the resources of the parent process. The parent may have to partition its resources among its children, or it may be able to share some resources, such as memory or files, among several of its children. Restricting a child process to a subset of the parent's resources prevents any process from overloading the system by creating too many child processes. In addition to supplying various physical and logical resources, the parent process may pass along initialization data input to the child process. For example, consider a process whose function is to display the contents of a file, say image.jpg, on the screen of a terminal. When the process is created, it will get as an input from its parent process the name of the file image.jpg. Using that file name, it will open the file and write the contents out. It may also get the name of the output device. Alternatively, some operating systems pass resources to child processes. On such a system, the new process may get two open files, image.jpg and the terminal device, and may simply transfer the datum between the two. When a process creates a new process, two possibilities for execution exist. The parent continues to execute concurrently with its children. The parent waits until some or all of its children have terminated. There are also two address space possibilities for the new process. The child process is a duplicate of the parent process. It has the same program and data as the parent. The child process has a new program loaded into it. To illustrate these differences, let's first consider the Unix operating system. In Unix, as we've seen, each process is identified by its process identifier, which is a unique integer. A new process is created by the fork function system call. The new process consists of a copy of the address space of the original process. This mechanism allows the parent process to communicate easily with its child process. Both processes, the parent and the child, continue execution at the instruction after the fork function, with one difference. The return code for the fork function is 0 for the new child process, whereas the non-zero process identifier of the child is returned to the parent. After a fork function system call, one of the two processes typically uses the execute function system call to replace the process's memory space with a new program. The execute function system call loads a binary file into memory, destroying the memory image of the program containing the execute function system call, and starts its execution. In this manner, the two processes are able to communicate and then go their separate ways. The parent can then create more children, or if it has nothing else to do while the child runs, it can use a wait function system call to move itself of the ready queue until the termination of the child. Because of the call to execute function overlays the process's address space with a new program, the call to execute function does not return control unless an error occurs. Program demonstrating process creation. Creating a separate process using the Unix fork function system call. The C program shown above illustrates the Unix system calls previously described. We now have two different processes running copies of the same program. The only difference is that the value of PID, the process identifier for the child process, is 0, while that for the parent is an integer value greater than 0. In fact, it is the actual PID of the child process. Diagram for the above program. Process creation using fork function system call. The child process inherits privileges and scheduling attributes from the parent as well as certain resources such as open files. The child process then overlays its address space with the Unix command /bin/ls used to get a directory listing using the execlp function system call. execlp function is a version of the execution function system call. The parent waits for the child process to complete with the wait function system call. When the child process completes by either implicitly or explicitly invoking exit function, the parent process resumes from the call to wait function, where it completes using the exit function system call. This is also illustrated in figure below. Of course, there is nothing to prevent the child from not invoking execution function and instead continuing to execute as a copy of the parent process. In this scenario, the parent and child are concurrent processes running the same code instructions. Because the child is a copy of the parent, each process has its own copy of any data. Program. Creating a separate process using the Windows API. Explanation for the above Windows program. Process creation in Windows. Processes are created in the Windows API using the create process function, which is similar to fork function in that a parent creates a new child process. However, whereas fork function has the child process inheriting the address space of its parent, create process function requires loading a specified program into the address space of the child process at process creation. Furthermore, whereas fork function is passed no parameters, create process function expects no fewer than 10 parameters. The C program shown above illustrates the create process function, which creates a child process that loads the application mspaint.execute. We opt for many of the default values of the 10 parameters passed to create process function. The 2 parameters passed to the create process function are instances of the startupinfo and process information structures. Startupinfo specifies many properties of the new process, such as window size and appearance, and handles to standard input and output files. The process information structure contains a handle and the identifiers to the newly created process and its thread. We invoke the zeroMemory function to allocate memory for each of these structures before proceeding with the create process function. The first 2 parameters passed to create process function are the application name and command line parameters. If the application name is null, as it is in this case, the command line parameter specifies the application to load. In this instance, we are loading the Microsoft Windows mspaint.execution application. Beyond these 2 initial parameters, we use the default parameters for inheriting process and thread handles, as well as specifying that there will be no creation flags. We also use the parent's existing environment block and starting directory. Last, we provide 2 pointers to the startup info and process information structures created at the beginning of the program. Process termination. A process terminates when it finishes executing its final statement and asks the operating system to delete it by using the exit function system call. At that point, the process may return a status value, typically an integer, to its parent process via the wait function system call. All the resources of the process, including physical and virtual memory, open files, and input-output buffers, are delocated by the operating system. Termination can occur in other circumstances as well. A process can cause the termination of another process via an appropriate system call, for example, terminate process function in Windows. Usually, such a system call can be invoked only by the parent of the process that is to be terminated. Otherwise, users could arbitrarily kill each other's jobs. Note that a parent needs to know the identities of its children if it is to terminate them. Thus, when one process creates a new process, the identity of the newly created process is passed to the parent. A parent may terminate the execution of one of its children for a variety of reasons such as these. The child has exceeded its usage of some of the resources that it has been allocated. To determine whether this has occurred, the parent must have a mechanism to inspect the state of its children. The task assigned to the child is no longer required. The parent is exiting and the operating system does not allow a child to continue if its parent terminates. Some systems do not allow a child to exit if its parent has terminated. In such systems, if a process terminates either normally or abnormally, then all of its children must also be terminated. This phenomenon, referred to as cascading termination, is normally initiated by the operating system. Example. To illustrate process execution and termination, consider that in Linux and Unix systems, we can terminate a process by using an exit function system call, providing an exit status as a parameter, is as shown below. In fact, under normal termination, exit function may be called either directly, as shown above, or indirectly by a return statement in main function. A parent process may wait for the termination of a child process by using the wait function system call. The wait function system call is passed a parameter that allows the parent to obtain the exit status of the child. This system call also returns the process identifier of the terminated child so that the parent can tell which of its children has terminated. PID, TPID, INT status, PID equals wait and status. When a process terminates, its resources are delocated by the operating system. However, its entry in the process table must remain there until the parent calls wait function because the process table contains the process's exit status. A process that has terminated but whose parent has not yet called wait function is known as a zombie process. All the processes transition to this state when they terminate, but generally they exist as zombies only briefly. Once the parent calls wait function, the process identifier of the zombie process and its entry in the process table are released. Now consider what would happen if a parent did not invoke wait function and instead terminated, thereby leaving its child processes as orphans. Linux and Unix address this scenario by assigning the init process as the new parent to orphan processes. The init process periodically invokes wait function, thereby allowing the exit status of any orphaned process to be collected and releasing the orphans process identifier and process table entry. Process scheduling. The objective of multi-programming is to have some process running at all times to maximize CPU utilization. The objective of time sharing is to switch the CPU among processes so frequently that users can interact with each program while it is running. To meet these objectives, the process scheduler selects an available process, possibly from a set of several available processes for program execution on the CPU. For a single processor system, there will never be more than one running process. If there are more processes, the rest will have to wait until the CPU is free and can be rescheduled. Scheduling queues. As processes enter the system, they are put into a job queue which consists of all processes in the system. The processes that are residing in main memory and are ready and waiting to execute are kept on a list called the ready queue. This queue is generally stored as a linked list. The ready queue header contains pointers to the first and final PCBs in the list. Each PCB includes a pointer field that points to the next PCB in the ready queue. The system also includes other queues. When a process is allocated the CPU, it executes for a while and eventually quits, is interrupted, or waits for the occurrence of a particular event, such as the completion of an input-output request. Suppose the process makes an input-output request to a shared device, such as a disk. Since there are many processes in the system, the disk may be busy with the input-output request of some other process. The process, therefore, may have to wait for the disk. The list of processes waiting for a particular input-output device is called a device queue. Each device has its own device queue. A common representation of process scheduling is a queuing diagram, such as that in the above diagram. Each rectangular box represents a queue. Two types of queues are present: the ready queue and a set of device queues. The circles represent the resources that serve the queues, and the arrows indicate the flow of processes in the system. A new process is initially put in the ready queue. It waits there until it is selected for execution or dispatched. Once the process is allocated the CPU and is executing, one of the several events could occur. The process could issue an input-output request and then be placed in an input-output queue. The process could create a new child process and wait for the child's termination. The process could be removed forcibly from the CPU as a result of an interrupt and be put back in the ready queue. In the first two cases, the process eventually switches from the waiting state to the ready state and is then put back in the ready queue. A process continues this cycle until it terminates, at which time it is removed from all queues and has its PCB and resources delocated. Schedulers. A process migrates among the various scheduling queues throughout its lifetime. The operating system must select, for scheduling purposes, processes from these queues in some fashion. The selection process is carried out by the appropriate scheduler. Often, in a batch system, more processes are submitted than can be executed immediately. These processes are spooled to a mass storage device, typically a disk, where they are kept for later execution. The long-term scheduler or job scheduler selects processes from this pool and loads them into memory for execution. The short-term scheduler or CPU scheduler selects from among the processes that are ready to execute and allocates a CPU to one of them. The primary distinction between these two schedulers lies in frequency of execution. The short-term scheduler must select a new process for the CPU frequently. A process may execute for only a few milliseconds before waiting for an input-output request. Often, the short-term scheduler executes at least once every 100 milliseconds because of the short term between executions. The short-term scheduler must be fast. If it takes 10 milliseconds to decide to execute a process for 100 milliseconds, then 10 divided by 100 plus 10 equals 9%. Of the CPU is being wasted simply for scheduling the work. The long-term scheduler executes much less frequently. Minutes may separate the creation of one new process and the next. The long-term scheduler controls the degree of multiprogramming, the number of processes in memory. If the degree of multiprogramming is stable, then the average rate of process creation must be equal to the average departure rate of processes leaving the system. Thus, the long-term scheduler may need to be invoked only when a process leaves the system because of the longer interval between executions. The long-term scheduler can afford to take more time to decide which process should be selected for execution. It is important that the long-term scheduler make a careful selection. In general, most processes can be described as either input-output bound or CPU bound. An input-output bound process is one that spends more of its time doing input-output than it spends doing computations. A CPU-bound process, in contrast, generates input-output requests infrequently, using more of its time doing computations. It is important that the long-term scheduler select a good process mix of input-output bound and CPU-bound processes. If all processes are input-output bound, the ready queue will almost always be empty and the short-term scheduler will have little to do. If all the processes are CPU-bound, the input-output waiting queue will almost always be empty, devices will go unused, and again the system will be unbalanced. The system with the best performance will thus have a combination of CPU-bound and input-output bound processes. On some systems, the long-term scheduler may be absent or minimal. For example, time-sharing systems such as Unix or Microsoft Windows systems often have no long-term scheduler but simply put every new process in memory for the short-term scheduler. The stability of these systems depends either on a physical limitation, such as the number of available terminals, or on the self-adjusting nature of human users. If performance declines to unacceptable levels on a multi-user system, some users will simply quit. Some operating systems, such as time-sharing systems, may introduce an additional, intermediate level of scheduling. This medium-term scheduler is diagrammed. The key idea behind a medium-term scheduler is that sometimes it can be advantageous to remove a process from memory and from active contention for the CPU and thus reduce the degree of multiprogramming. Later, the process can be reintroduced into memory and its execution can be continued where it left off. This scheme is called swapping. The process is swapped out and is later swapped in by the medium-term scheduler. Swapping may be necessary to improve the process mix or because a change in memory requirements has overcommitted available memory, requiring memory to be freed up. Context switch. Interrupts cause the operating system to change a CPU from its current task and to run a kernel routine. Such operations happen frequently on general-purpose systems. When an interrupt occurs, the system needs to save the current context of the process running on the CPU so that it can restore that context when its processing is done, essentially suspending the process and then resuming it. The context is represented in the PCB of the process. It includes the value of the CPU registers, the process state, and the memory management information. Generically, we perform a state save of the current state of the CPU, be it in a kernel or user mode, and then a state restore to resume operations. Switching the CPU to another process requires performing a state save of the current process and a state restore of a different process. This task is known as a context switch. When a context switch occurs, the kernel saves the context of the old process in its PCB and loads the saved context of the new process scheduled to run. Context switch time is pure overhead because the system does no useful work while switching. Switching speed varies from machine to machine depending on the memory speed, the number of registers that must be copied, and the existence of special instructions such as a single instruction to load or store all registers. A typical speed is a few milliseconds. context switch times are highly dependent on hardware support. For instance, some processes such as the Sun Ultra Spark provide multiple sets of registers. A context switch here simply requires changing the pointer to the current register set. Of course, if there are more active processes than there are register sets, the system resorts to copying register data to and from memory as before. Also, the more complex the operating system, the greater the amount of work that must be done during a context switch. For instance, the address space of the current process must be preserved as the space of the next task is prepared for use. How the address space is preserved and what amount of work is needed to preserve it depend on the memory management method of the operating system. Process synchronization. In this chapter, we discuss various mechanisms to ensure the orderly execution of cooperating processes that share a logical address space so that data consistency is maintained. We've already seen that processes can execute concurrently or in parallel. This means that one process may only partially complete execution before another process is scheduled. In fact, a process may be interrupted at any point in its instruction stream, and the processing core may be assigned to execute instructions of another process. Consider the bounded buffer. Our original solution allowed at most buffer size. One item in the buffer at the same time. Suppose we want to modify the algorithm to remedy this deficiency. One possibility is to add an integer variable counter initialized to 0. Counter is incremented every time we add a new item to the buffer and is decremented every time we remove one item from the buffer. The code for the producer process can be modified as follows. Although the producer and consumer routines shown above are correct separately, they may not function correctly when executed concurrently. As an illustration, suppose that the value of the variable counter is currently 5 and that the producer and consumer processes concurrently execute the statements counter plus plus and counter following. Following the execution of these two statements, the value of the variable counter may be 4, 5, or 6. The only correct result, though, is counter equals 5, which is generated correctly if the producer and consumer execute separately. Implementation of above program in machine language. We can show that the value of counter may be incorrect as follows. Note that the statement counter plus plus may be implemented in machine language on a typical machine as follows. Register 1 equals counter, register 1 equals register 1 plus 1, counter equals register 1, where register 1 is one of the local CPU registers. Similarly, the statement counter minus minus is implemented as follows. Register 2 equals counter, register 2 equals register 2 minus 1, counter equals register 2, where again register 2 is one of the local CPU registers. Even though register 1 and register 2 may be the same physical register, an accumulator say, remember that the contents of this register will be saved and restored by the interrupt handler. The concurrent execution of counter plus plus and counter minus minus is equivalent to a sequential execution in which the lower level statements presented previously are interleaved in some arbitrary order, but the order within each high level statement is preserved. One such interleaving is the following. T0. Producer execute register 1 equals counter, brackets register 1 equals 5. T1. Producer execute register 1 equals register 1 plus 1, brackets register 1 equals 6, close brackets. T2. Consumer execute register 2 equals counter, open brackets register 2 equals 5, close brackets. T3, consumer execute register 2 equals register 2 minus 1, open brackets, register 2 equals 4, close brackets. T4, producer execute counter equals register 1, open brackets, counter equals 6, close brackets. T5, consumer execute counter equals register 2, open brackets, counter equals 4, close brackets. Notice that we have arrived at the incorrect state counter equals 4, indicating that 4 buffers are full when in fact 5 buffers are full. If we reversed the order of the statements at T4 and T5, we would arrive at the incorrect state counter equals 6. We would arrive at this incorrect state because we allowed both processes to manipulate the variable counter concurrently. A situation where several processes access and manipulate the same data concurrently and the outcome of the execution depends on the particular order in which the access takes place is called a race condition. To guard against the race condition above, we need to ensure that only one process at a time can be manipulating the variable counter. To make such a guarantee, we require that the processes be synchronized in some way. In multi-threaded applications, several threads, which are quite possibly sharing data, are running in parallel on different processing cores. Clearly, we want any changes that result from such activities not to interfere with one another, process synchronization and coordination among cooperating processes. Process concept. A question that arises in discussing operating systems involves what to call all the CPU activities. A batch system executes jobs, whereas a time-shared system has user programs or tasks. Even on a single user system, a user may be able to run several programs at one time, a word processor, a web browser, and an email package. And even if a user can execute only one program at a time, such as on an embedded device that does not support multitasking, the operating system may need to support its own internal programmed activities such as memory management. In many respects, all these activities are similar, so we call all of them processes. The terms job and process are used almost interchangeably in this text. Although we personally prefer the term process, much of operating system theory and terminology was developed during a time when the major activity of operating systems was job processing. It would be misleading to avoid the use of commonly accepted terms that include the word job, such as job scheduling, simply because process has superseded job. A process is more than the program code, which is sometimes known as the text section. It also includes the current activity as represented by the value of the program counter and the contents of the process's registers. A process generally also includes the process stack, which contains temporary data such as function parameters, return addresses, and local variables, and a data section, which contains global variables. A process may also include a heap, which is memory that is dynamically allocated during process runtime. The structure of a process in memory is shown below. We emphasize that a program by itself is not a process. A program is a passive entity such as a file containing a list of instructions stored on disk, often called an executable file. In contrast, a process is an active entity with a program counter specifying the next instruction to execute and a set of associated resources. A program becomes a process when an executable file is loaded into memory. Two common techniques for loading executable files: name of the executable file on the command line, as in prog.exe or a.out. Although two processes may be associated with the same program, they are nevertheless considered two separate execution sequences. For instance, Several users may be running different copies of the mail program, or the same user may invoke many copies of the web browser program. Each of these is a separate process. Although the text sections are equivalent, the data, heap, and the stack sections vary. It is also common to have a process that spawns many processes as it runs. Note that a process itself can be an execution environment for other code. The Java programming environment provides a good example. In many circumstances, an executable Java program is executed within the Java Virtual Machine (JVM). The JVM executes as a process that interprets the loaded Java code and takes actions via the native machine instructions on behalf of that code. For example, to run the compiled Java program, program.class, we would enter Java program. The command Java runs the JVM as an ordinary process, which in turn executes the Java program in the virtual machine. The concept is the same as simulation, except that the code, instead of being written for a different instruction set, is written in the Java language. Process state. As a process executes, it changes state. The state of a process is defined in part by the current activity of that process. A process may be in one of the following states. New. The process is being created. Running. The instructions are being executed. Waiting. The process is waiting for some event to occur, such as an input-output completion or reception of a signal. Ready. The process is waiting to be assigned to a processor. Terminated. The process has finished execution. These names are arbitrary and they vary across operating systems. The states that they represent are found on all systems, however. Certain operating systems also more finely delineate process states. It is important to realize that only one process can be running on any processor at any instant. Many processes may be ready and waiting, however. Process control block. Each process is represented in the operating system by a process control block, PCB, also called a task control block. It contains many pieces of information associated with a specific process, including these. Process state. The state may be new, ready, running, waiting, halted, and so on. Process control block. Each process is represented in the operating system by a process control block, PCB, also called a task control block. A PCB is shown below. It contains many pieces of information associated with a specific process, including these. Process state. The state may be new, ready, running, waiting, halted, and so on. Program counter. The counter indicates the address of the next instruction to be executed for this process. CPU registers. The registers vary in number and type depending on the computer architecture. They include accumulators, index registers, stack pointers, and general-purpose registers, plus any condition code information. Along with the program counter, this state information must be saved when an interrupt occurs to allow the process to be continued correctly afterward. CPU scheduling information. This information includes a process priority, pointers to scheduling queues, and any other scheduling parameters. Memory management information. This information may include such items as the value of the base and limit registers and the page tables or the segment tables depending on the memory system used by the operating system. Diagram showing how CPU shifts between processes. Accounting information. This information includes the amount of CPU and real-time used, time limits, account numbers, job or process numbers, and so on. Input-output status information. This information includes the list of input-output devices allocated to the process, a list of open files, and so on. In brief, the PCB simply serves as the repository of any information that may vary from process to process. Threads. The process model discussed so far has implied that a process is a program that performs a single thread of execution. For example, when a process is running a word processor program, a single thread of instructions is being executed. The single thread of control allows the process to perform only one task at a time. The user cannot simultaneously type in characters or run the spell checker within the same process, for example. Most modern operating systems have extended the process concept to allow a process to have multiple threads of execution and thus to perform more than one task at a time. This feature is especially beneficial on multi-core systems where multiple threads can run in parallel. On a system that supports threads, the PCB is expanded to include information for each thread. Other changes throughout the system are also needed to support threads. Processes. Early computers allowed only one program to be executed at a time. This program had complete control of the system and had access to all the system's resources. In contrast, contemporary computer systems allow multiple programs to be loaded into memory and executed concurrently. This evolution required firmer control and more compartmentalization of the various programs, and these needs resulted in the notion of a process, which is a program in execution. A process is the unit of work in a modern time-sharing system. A system, therefore, consists of a collection of processes: operating system process, executing system code, user processes, executing user code. Potentially, all these processes can execute concurrently with the CPU or CPUs multiplexed among them. By switching the CPU between processes, the operating system can make the computer more productive. A process can be thought of as a program in execution. A process will need certain resources such as CPU time, memory, files, and input-output devices to accomplish its task. These resources are allocated to the process either when it is created or while it is executing. A process is the unit of work in most systems. Although traditionally a process contained only a single thread of control as it ran, most modern operating systems now support processes that have multi-threads. The operating system is responsible for several important aspects of process and thread management: the creation and deletion of both user and system processes, the scheduling of processes, and the provision of mechanisms for synchronization, communication, and deadlock handling for processes. Real-time scheduling. Real-time CPU scheduling. CPU scheduling for real-time operating systems involves special issues. In general, we can distinguish between soft real-time systems and hard real-time systems. Soft real-time systems provide no guarantee as to when a critical real-time process will be scheduled. They guarantee only that the process will be given preference over non-critical processes. Hard real-time systems have stricter requirements. A task must be serviced by its deadline. Service after the deadline has expired is the same as no service at all. We explore several issues related to process scheduling in both soft and hard real-time operating systems. Minimizing latency. Consider the event-driven nature of a real-time system. The system is typically waiting for an event in real time to occur. Events may arise either in software, as when a timer expires, or in hardware, as when a remote-controlled vehicle detects that it is approaching an obstruction. When an event occurs, the system must respond to and service it as quickly as possible. We refer to event latency as the amount of time that elapses from when an event occurs to when it is serviced. See the figure below. Usually, different events have different latency requirements. For example, the latency requirement for an anti-lock brake system might be 3 to 5 milliseconds. That is, from the time a wheel first detects that it is sliding, the system controlling the anti-lock brakes has 3 to 5 milliseconds to respond to and control the situation. Any response that takes longer might result in the automobiles veering out of control. In contrast, an embedded system controlling radar in an airliner might tolerate a latency period of several seconds. Two types of latencies affect the performance of real-time systems. 1. Interrupt latency. 2. Dispatch latency. Interrupt latency. It refers to the period of time from the arrival of an interrupt at the CPU to the start of the routine that services the interrupt. When an interrupt occurs, the operating system must first complete the instruction it is executing and determine the type of interrupt that occurred. It must then save the state of the current process before servicing the interrupt using the specific interrupt service routine, ISR. The total time required to perform these tasks is the interrupt latency. Obviously, it is crucial for real-time operating systems to minimize interrupt latency to ensure that real-time tasks receive immediate attention. Indeed, for hard real-time systems, interrupt latency must not simply be minimized, it must be bounded to meet the strict requirements of these systems. One important factor contributing to interrupt latency is the amount of time interrupts may be disabled while kernel data structures are being updated. Real-time operating systems require that interrupts be disabled for only very short periods of time. Dispatch latency. The amount of time required for the scheduling dispatcher to stop one process and start another is known as dispatch latency. Providing real-time tasks with immediate access to the CPU mandates that real-time operating systems minimize this latency as well. The most effective technique for keeping dispatch latency low is to provide preemptive kernels. The conflict phase of dispatch latency has two components. 1. Preemption of any process running in the kernel. 2. Release by low-priority processes of resources needed by a high-priority process. As an example, in Solaris, the dispatch latency with preemption disabled is over 100 milliseconds. With preemption enabled, it is reduced to less than a millisecond. Priority-based scheduling. The most important feature of a real-time operating system is to respond immediately to a real-time process as soon as that process requires the CPU. As a result, the scheduler for a real-time operating system must support a priority-based algorithm with preemption. If the scheduler also supports preemption, a process currently running on the CPU will be preempted if a higher priority process becomes available to run. Each of these systems assigns real-time processes the highest scheduling priority. For example, Windows has 32 different priority levels. The highest levels, priority values 16 to 31, are reserved for real-time processes. Solaris and Linux have similar prioritization schemes. A preemptive priority-based scheduler only guarantees soft real-time functionality. Hard real-time systems must further guarantee that real-time tasks will be serviced in accord with their deadline requirements, and making such guarantees requires additional scheduling features. Before we proceed with the details of the individual schedulers, however, we must define certain characteristics of the processes that are to be scheduled. First, the processes are considered periodic. That is, they require the CPU at constant intervals, periods. Once a periodic process is acquired, the CPU, it has a fixed processing time, T, a deadline, D, by which it must be serviced by the CPU, and a period, P. The relationship of the processing time, the deadline, and the period can be expressed as 0 is less than or equal to T, which is less than or equal to D, which is less than or equal to P. The rate of a periodic task is 1 over P. Figure illustrates the execution of a periodic process over time. Schedulers can take advantage of these characteristics and assign priorities according to a process's deadline or rate requirements. What is unusual about this form of scheduling is that a process may have to announce its deadline requirements to the scheduler. Then, using a technique known as an admission control algorithm, the scheduler does one of two things. It either admits the process, guaranteeing that the process will complete on time, or rejects the request as impossible if it cannot guarantee that the task will be serviced by its deadline. Rate monotonic scheduling. The rate monotonic scheduling algorithm schedules periodic tasks using a static priority policy with preemption. If a lower priority process is running and a higher priority process becomes available to run, it will preempt the lower priority process. Upon entering the system, each periodic task is assigned a priority inversely based on its period. The shorter the period, the higher the priority. The longer the period, the lower the priority. The rationale behind this policy is to assign a higher priority to tasks that require the CPU more often. Furthermore, rate monotonic scheduling assumes that the processing time of a periodic process is the same for each CPU burst. That is, every time a process acquires the CPU, the duration of its CPU burst is the same. Let's consider an example. We have two processes, P1 and P2. The periods for P1 and P2 are 50 and 100, respectively. That is, P1 equals 50 and P2 equals 100. The processing times are T1 equals 20 for P1 and T2 equals 35 for P2. The deadline for each process requires that it complete its CPU burst by the start of its next period. We must first ask ourselves whether it is possible to schedule these tasks so that each meets its deadlines. If we measure the CPU utilization of a process Pi as the ratio of its burst to its period, Ti over Pi, the CPU utilization of P1 is 20 over 50, equaling to 0.40. That of P2 is 35 over 100, equaling 0.35, for a total CPU utilization of 75%. Therefore, it seems we can schedule these tasks in such a way that both meet their deadlines and still leave the CPU with available cycles. Suppose we assume P2 a higher priority than P1. The execution of P1 and P2 in this situation is shown in figure. As we can see, P2 starts execution first and completes at time 35. At this point, P1 starts. It completes its CPU burst at time 55. However, the first deadline for P1 was at time 50, so the scheduler has caused P1 to miss its deadline. Example of rate monotonic scheduling. Now suppose we use rate monotonic scheduling in which we assign P1 a higher priority than P2 because the period of P1 is shorter than that of P2. The execution of these processes in this situation is shown in figure. P1 starts first and completes its CPU burst at a time 20, thereby meeting its first deadline. P2 starts running at this point and runs until time 50. At this time, it is preempted by P1, although it still has 5 milliseconds remaining in its CPU burst. P1 completes its CPU burst at time 70, at which point the scheduler resumes P2. P2 completes its CPU burst at time 75, also meeting its first deadline. The system is idle until time 100 when P1 is scheduled again. Rate monotonic scheduling is considered optimal in that if a set of processes cannot be scheduled by this algorithm, it cannot be scheduled by any other algorithm that assigns static priorities. Let's next examine a set of processes that cannot be scheduled using the rate monotonic algorithm. Assume that process P1 has a period of P1 equaling 50 and a CPU burst of T1 equaling 25. For P2, the corresponding values are P2 equaling 80 and T2 equaling 35. Rate monotonic scheduling would assign process P1 a higher priority as it has the shorter period. The total CPU utilization of the two processes is 25 divided by 50 plus 35 divided by 80 equaling 0.94, and it therefore seems logical that the two processes could be scheduled and still leave the CPU with 6% available time. Figure below shows the scheduling of processes P1 and P2. Initially, P1 runs until it completes its CPU burst at time 25. Process P2 then begins running and runs until time 50 when it is preempted by P1. At this point, P2 still has 10 milliseconds remaining in its CPU burst. Process P1 runs until time 75. Consequently, P2 misses the deadline for completion of its CPU burst at time 80. Limitations of rate monotonic scheduling. CPU utilization is bounded and it is not always possible fully to maximize CPU resources. The worst-case CPU utilization for scheduling n processes is n brackets 2 to the power of 1 divided by n minus 1 close brackets. With one process in the system, CPU utilization is 100%, but it falls to approximately 69% as the number of processes approaches infinity. With two processes, CPU utilization is bounded at about 83%. Combined CPU utilization for the two processes scheduled above is 75%. Therefore, the rate monotonic scheduling algorithm is guaranteed to schedule them so that they can meet their deadlines. For the two processes scheduled in figure above, combined CPU utilization is approximately 94%. Therefore, rate monotonic scheduling cannot guarantee that they can be scheduled so that they meet their deadlines. Earliest deadline first scheduling. Earliest deadline first EDF scheduling dynamically assigns priorities according to deadline. The earlier the deadline, the higher the priority. The later the deadline, the lower the priority. Under the EDF policy, when a process becomes runnable, it must announce its deadline requirements to the system. Priorities may have to be adjusted to reflect the deadline of the newly runnable process. Note how this differs from the rate monotonic scheduling where priorities are fixed. To illustrate EDF scheduling, we again schedule the processes shown in missing deadlines for rate monotonic scheduling figure which failed to meet deadline requirements under rate monotonic scheduling. Recall that P1 has values of P1 equaling 50 and T1 equaling 25, and that P2 has values of P2 equaling 80 and T2 equaling 35. Process P1 has the earliest deadline, so its initial priority is higher than that of process P2. Process P2 begins running at the end of the CPU burst for P1. However, whereas rate monotonic scheduling allows P1 to preempt P2 at the beginning of its next period at time 50, EDF scheduling allows process P2 to continue running. P2 now has a higher priority than P1 because its next deadline at time 80 is earlier than that of P1 at time 100. Thus, both P1 and P2 meet their first deadlines. Process P1 again begins running at time 60 and completes its second CPU burst at time 85, also meeting its second deadline at time 100. P2 begins running at this point only to be preempted by P1 at the start of its next period at time 100. P2 is preempted because P1 has an earlier deadline, time 150, than P2, time 160. At time 125, P1 completes its CPU burst and P2 resumes execution, finishing at time 145 and meeting its deadline as well. The system is idle until time 150 when P1 is scheduled to run once again. Unlike the rate monotonic algorithm, EDF scheduling does not require that processes be periodic, nor must a process require a constant amount of CPU time per burst. The only requirement is that a process announce its deadline to the scheduler when it becomes runnable. The appeal of EDF scheduling is that it is theoretically optimal. Theoretically, it can schedule processes so that each process can meet its deadline requirements and CPU utilization will be 100%. In practice, however, it is impossible to achieve this level of CPU utilization due to the cost of context switching between processes and interrupt handling. Proportional share scheduling. Proportional share schedulers operate by allocating T shares among all applications. An application can receive N shares of time, thus ensuring that the application will have N over T of the total processor time. As an example, assume that a total of T equaling 100 shares is to be divided among three processes A, B, and C. A is assigned 50 shares, B is assigned 15 shares, and C is assigned 20 shares. This scheme ensures that A will have 50% of total processor time, B will have 15%, and C will have 20%. Proportional share schedulers must work in conjunction with an admission control policy to guarantee that an application receives its allocated shares of time. An admission control policy will admit a client requesting a particular number of shares only if sufficient shares are available. In our current example, we have allocated 50 plus 15 plus 20 equaling 85 shares of the total of 100 shares. If a new process D requested 30 shares, the admission controller would deny D entry into the system. POSIX real-time scheduling. The POSIX standard also provides extensions for real-time computing POSIX.1b. POSIX defines two scheduling classes for real-time threads: SCHED FIFO, SCHED RR. SCHED FIFO schedules threads according to a first-come, first-served policy using a FIFO queue. However, there is no time slicing among threads of equal priority. Therefore, the highest priority real-time thread at the front of the FIFO queue will be granted the CPU until it terminates or blocks. SCHED RR uses a round-robin policy. It is similar to a SCHED FIFO except that it provides time slicing among threads of equal priority. POSIX provides an additional scheduling class, SCHED Other, but its implementation is undefined and system-specific. It may behave differently on different systems. The POSIX API specifies the following two functions for getting and setting the scheduling policy: pthread attr get SCHED policy brackets pthread attr t asterisk attr int asterisk policy close brackets. Pthread attr set CHED policy open brackets pthread attr t asterisk attr int policy close brackets. The first parameter to both functions is a pointer to the set of attributes for the thread. The second parameter is either 1. A pointer to an integer that is set to the current scheduling policy for pthread attr get SCHED policy function, or 2. An integer value SCHED FIFO, SCHED RR, or SCHED Other for the pthread ATTR set SCHED policy function. Both functions return non-zero values if any error occurs. Program POSIX Real-Time Scheduling API. Here we illustrate a POSIX pthread program using this API. This program first determines the current scheduling policy and then sets the scheduling algorithm to SCHED FIFO. Recovery from deadlock. When a detection algorithm determines that a deadlock exists, several alternatives are available. One possibility is to inform the operator that a deadlock has occurred and to let the operator deal with the deadlock manually. Another possibility is to let the system recover from the deadlock automatically. There are two options for breaking a deadlock. One is simply to abort one or more processes to break the circular wait. The other is to preempt some resources from one or more of the deadlocked processes. Process termination. To eliminate deadlocks by aborting a process, we use one of two methods. In both methods, the system reclaims all resources allocated to the terminated process. Abort all deadlocked processes. This method clearly will break the deadlock cycle, but at great expense. The deadlocked processes may have computed for a long time, and the results of these partial computations must be discarded and probably will have to be recomputed later. Abort one process at a time until the deadlock cycle is eliminated. This method occurs considerable overhead since after each process is aborted, a deadlock detection algorithm must be invoked to determine whether any processes are still deadlocked. Aborting a process may not be easy. If the process was in the midst of updating a file, terminating it will leave that file in an incorrect state. Similarly, if the process was in the midst of printing data on a printer, the system must reset the printer to a correct state before printing the next job. If the partial termination method is used, then we must determine which deadlocked process or processes should be terminated. This determination is a policy decision similar to CPU scheduling decision. The question is basically an economic one. We should abort those processes whose termination will occur at the minimum cost. Unfortunately, the term minimum cost is not a precise one. Many factors may affect which process is chosen, including what the priority of the process is, how long the process has computed, and how much longer the process will compute before completing its designated task, how many and what types of resources the process has used, for example, whether the resources are simple to preempt, how many more resources the process needs in order to complete, how many processes will need to be terminated, whether the process is interactive or batch. Resource preemption. To eliminate deadlocks using resource preemption, we successively preempt some resources from processes and give these resources to other processes until the deadlock cycle is broken. If preemption is required to deal with deadlocks, then three issues need to be addressed. 1. Selecting a victim. Which resources and which processes are to be preempted? As in process termination, we must determine the order of preemption to minimize cost. Cost factors may include such parameters as the number of resources a deadlocked process is holding and the amount of time the process has thus far consumed. 2. Rollback. If we preempt a resource from a process, what should be done with that process? Clearly, it cannot continue with its normal execution. It is missing some needed resource. We must roll back the process to some safe state and restart it from that state. Since, in general, it is difficult to determine what a safe state is, The simplest solution is a total rollback. Abort the process and then restart it. Although it is more effective to roll back the process only as far as necessary to break the deadlock, this method requires the system to keep more information about the state of all running processes. 3. How do we ensure that starvation will not occur? That is, how can we guarantee that resources will not always be preempted from the same process? In a system where victim selection is based primarily on cost factors, it may happen that the same process is always picked as a victim. As a result, this process never completes its designated task, a starvation situation any practical system must address. Clearly, we must ensure that a process can be picked as a victim only a small, finite number of times. The most common solution is to include the number of rollbacks in the cost factor. Scheduling algorithms. CPU scheduling deals with the problem of deciding which of the processes in the ready queue is to be allocated to the CPU. There are many different CPU scheduling algorithms. They are listed as follows. 1. First come, first serve scheduling. 2. Shortest job first scheduling. 3. Priority scheduling. 4. Round-robin scheduling. 5. Multi-level queue scheduling. 6. Multi-level feedback queue scheduling. First come, first served scheduling. By far, the simplest CPU scheduling algorithm is the first come, first served FCFS scheduling algorithm. With this scheme, the process that requests the CPU first is allocated the CPU first. The implementation of the FCFS policy is easily managed with a first-in, first-out queue. When a process enters the ready queue, its PCB is linked onto the trail of the queue. When the CPU is free, it is allocated to the process at the head of the queue. The running process is then removed from the queue. The code for FCFS scheduling is simple to write and understand. On the negative side, the average waiting time under the FCFS policy is often quite long. Consider the following set of processes that arrive at time 0 with the length of the CPU burst given in milliseconds. If the processes arrive in the order P1, P2, P3 and are served in FCFS order, we get the results shown in the following Gantt chart, which is a bar chart that illustrates a particular schedule, including the start and finish times of each of the participating processes. The waiting time is 0 milliseconds for process P1, 24 milliseconds for process P2, and 27 milliseconds for process P3. Thus, the average waiting time is 0 plus 24 plus 27 divided by 3 equaling 17 milliseconds. Gantt chart with arrival time. If the processes arrive in the order P2, P3, P1, however, the results will be as shown in the following Gantt chart. The average waiting time is now 6 plus 0 plus 3 divided by 3 equaling 3 milliseconds. This reduction is substantial. Thus, the average waiting time under the FCFS policy is generally not minimal and may vary substantially if the process's CPU burst times vary greatly. In addition, consider the performance of FCFS scheduling in a dynamic situation. Assume we have one CPU-bound process and many input-output-bound processes. As the processes flow around the system, the following scenario may result. The CPU-bound process will get and hold the CPU. During this time, all the other processes will finish their input-output and will move into the ready queue, waiting for the CPU. While the processes wait in the ready queue, the input-output devices idle. Eventually, the CPU-bound process finishes its CPU burst and moves to an input-output device. All the input-output bound processes which have short CPU bursts execute quickly and move back to the input-output queues. At this point, the CPU sits idle. The CPU-bound process will then move back to the ready queue and be allocated the CPU. Again, all the input-output processes end up waiting in the ready queue until the CPU-bound process is done. There is a convoy effect as all the other processes wait for the one big process to get off the CPU. This effect results in lower CPU and device utilization than might be possible if the shorter processes were allowed to go first. FCFS scheduling algorithm is non-preemptive. Once the CPU has been allocated to a process, that process keeps the CPU until it releases the CPU either by terminating or by requesting input-output. The FCFS algorithm is thus particularly troublesome for time-sharing systems where it is important that each user get a share of the CPU at regular intervals. It would be disastrous to allow one process to keep the CPU for an extended period. Shortest job first scheduling. A different approach to CPU scheduling is the shortest job first SJF scheduling algorithm. This algorithm associates with each process the length of the process's next CPU burst. When the CPU is available, it is assigned to the process that has the smallest next CPU burst. If the next CPU bursts of two processes are the same, FCFS scheduling is used to break the tie. Note that a more appropriate term for this scheduling method would be the shortest next CPU burst algorithm, because scheduling depends on the length of the next CPU burst of a process rather than its total length. As an example of SJF scheduling, consider the following set of processes with the length of the CPU burst given in milliseconds. Process P1, burst time 6. Process P2, burst time 8. Process P3, burst time 7. Process P4, burst time 3. Using SJF scheduling, we would schedule these processes according to the following Gantt chart. The waiting time is 3 milliseconds for process P1, 16 milliseconds for process P2, 9 milliseconds for process P3, and 0 milliseconds for process P4. Thus, the average waiting time is 3 plus 16 plus 9 plus 0 divided by 4 equaling 7 milliseconds. By comparison, if we were using the FCFS scheduling scheme, the average waiting time would be 10.25 milliseconds. The SJF scheduling algorithm is provably optimal in that it gives the minimum average waiting time for a given set of processes. Moving a short process before a long one decreases the waiting time of the short process more than it increases the waiting time of the long process. Consequently, the average waiting time decreases. The real difficulty with the SJF algorithm is knowing the length of the next CPU request. For long-term job scheduling in a batch system, we can use the process time limit that a user specifies when he submits the job. In this situation, users are motivated to estimate the process time limit accurately, since a lower value may mean faster response, but too low a value will cause a time limit exceeded error and require resubmission. SJF scheduling is used frequently in long-term scheduling. Although the SJF algorithm is optimal, it cannot be implemented at the level of short-term CPU scheduling. With short-term scheduling, there is no way to know the length of the next CPU burst. One approach to this problem is to try to approximate SJF scheduling. We may not know the length of the next CPU burst, but we may be able to predict its value. We expect that the next CPU burst will be similar in length to the previous ones. By computing an approximation of the length of the next CPU burst, we can pick the process with the shortest predicted CPU burst. The next CPU burst is generally predicted as an exponential average of the measured lengths of previous CPU bursts. Prediction of the length of the next CPU burst. The SJF algorithm can be either preemptive or non-preemptive. The choice arises when a new process arrives at the ready queue while a previous process is still executing. The next CPU burst of the newly arrived process may be shorter than what is left of the currently executing process. The preemptive SJF algorithm will preempt the currently executing process, whereas a non-preemptive SJF algorithm will allow the currently running process to finish its CPU burst. Shortest remaining time first scheduling. Preemptive SJF scheduling is sometimes called shortest remaining time first scheduling. As an example, consider the following 4 processes with the length of the CPU burst given in milliseconds. Process P1, arrival time 0, burst time 8. Process P2, arrival time 1, burst time 4. Process P3, arrival time 2, burst time 9. Process P4, arrival time 3, burst time 5. If the processes arrive at the ready queue at the times shown and need the indicated burst times, then the resulting preemptive SJF schedule is as depicted in the following Gantt chart. Process P1 is started at time 0 since it is the only process in the queue. Process P2 arrives at time 1. The remaining time for process P1, 7 milliseconds, is larger than the time required by process P2, 4 milliseconds, so process P1 is preempted and process P2 is scheduled. The average waiting time for this example is open brackets 10 minus 1 close brackets plus open brackets 1 minus 1 close brackets plus open brackets 17 minus 2 close brackets plus open brackets 5 minus 3 close brackets divided by 4 equaling to 26 divided by 4 equaling to 6.5 milliseconds. Non-preemptive SJF scheduling would result in an average waiting time of 7.75 milliseconds. Priority scheduling. The SJF algorithm is a special case of the general priority scheduling algorithm. A priority is associated with each process and the CPU is allocated to the process with the highest priority. Equal priority processes are scheduled in FCFS order. An SJF algorithm is simply a priority algorithm where the priority P is the inverse of the predicted next CPU burst. The larger the CPU burst, the lower the priority, and vice versa. Note that we discuss scheduling in terms of high priority and low priority. Priorities are generally indicated by some fixed range of numbers such as 0 to 7 or 0 to 4095. However, there is no general agreement on whether 0 is the highest or lowest priority. Some systems use low numbers to represent low priority, others use low numbers for high priority. This difference can lead to confusion. In this text, we assume that low numbers represent high priority. As an example, consider the following set of processes assumed to have arrived at time 0 in the order of P1, P2, so forth till P5, with the length of the CPU burst given in milliseconds. Process P1, burst time 10, priority 3. Process P2, burst time 1, priority 1. Process P3, burst time 2, priority 4. Process P4, burst time 1, priority 5. Process P5, burst time 5, priority 2. Using priority scheduling, we would schedule these processes according to the following Gantt chart. The average waiting time is 8.2 milliseconds. Priorities can be defined either internally or externally. Internally defined priorities use some measurable quantity or quantities to compute the priority of a process. For example, time limits, memory requirements, the number of open files, and the ratio of average input-output burst to average CPU burst have been used in computing priorities. External priorities are set by criteria outside the operating system, such as the importance of the process, the type and amount of funds being paid for computer use, the department sponsoring the work, and other, often political factors. Priority scheduling can be either preemptive or non-preemptive. When a process arrives at the ready queue, its priority is compared with the priority of the currently running process. A preemptive priority scheduling algorithm will preempt the CPU if the priority of the newly arrived process is higher than the priority of the currently running process. A non-preemptive priority scheduling algorithm will simply put the new process at the head of the ready queue. A major problem with priority scheduling algorithms is indefinite blocking or starvation. A process that is ready to run but waiting for the CPU can be considered blocked. A priority scheduling algorithm can leave some low-priority processes waiting indefinitely. In a heavily loaded computer system, a steady stream of higher priority processes can prevent a low-priority process from ever getting the CPU. Generally, one of the two things will happen. Either the process will eventually be run, or the computer system will eventually crash and lose all unfinished low-priority processes. A solution to the problem of indefinite blockage of low-priority process is aging. Aging involves gradually increasing the priority of processes that wait in the system for a long time. For example, if priorities range from 127 low to 0 high, we could increase the priority of a waiting process by 1 every 15 minutes. Eventually, even a process with an initial priority of 127 would have the highest priority in the system and would be executed. In fact, it would take no more than 32 hours for a priority 127 process to age to a priority 0 process. Round-robin scheduling. The round-robin RR scheduling algorithm is designed especially for time-sharing systems. It is similar to FCFS scheduling, but preemption is added to enable the system to switch between processes. A small unit of time called a time quantum or time slice is defined. A time quantum is generally from 10 to 100 milliseconds in length. The ready queue is treated as a circular queue. The CPU scheduler picks the first process from the ready queue, sets a timer to interrupt after one time quantum, and dispatches the process. One of the two things will then happen. The process may have a CPU burst of less than one time quantum. In this case, the process itself will release the CPU voluntarily. The scheduler will then proceed to the next process in the ready queue. If the CPU burst of the currently running process is longer than one time quantum, the timer will go off and will cause an interrupt to the operating system. A context switch will be executed and the process will be put at the tail of the ready queue. The CPU scheduler will then select the next process in the ready queue. Consider the following set of processes that arrive at time 0 with the length of the CPU burst given in milliseconds. Process P1, burst time 24, process P2, burst time 3, process P3, burst time 3. If we use a time quantum of 4 milliseconds, then process P1 gets the first 4 milliseconds. Since it requires another 20 milliseconds, it is preempted after the first time quantum and the CPU is given to the next process in the queue, process P2. Process P2 does not need 4 milliseconds, so it quits before its time quantum expires. The CPU is then given to the next process, process P3. Once each process has received one time quantum, the CPU is returned to process P1 for an additional time quantum. The resulting RR schedule is as follows. Let's calculate the average waiting time for this schedule. P1 waits for 6 milliseconds, that is 10 minus 4. P2 waits for 4 milliseconds and P3 waits for 7 milliseconds. Thus, the average waiting time is 17 divided by 3, equaling 5.66 milliseconds. In the RR scheduling algorithm, no process is allocated the CPU for more than one time quantum in a row unless it is the only runnable process. If a process's CPU burst exceeds one time quantum, that process is preempted and is put back in the ready queue. The RR scheduling algorithm is thus preemptive. If there are n processes in the ready queue and the time quantum is q, then each process gets 1 divided by n of the CPU time in chunks of at most q time units. Each process must wait no longer than n minus 1 into q time units until its next time quantum. For example, with 5 processes and a time quantum of 20 milliseconds, each process will get up to 20 milliseconds every 100 milliseconds. The performance of the RR algorithm depends heavily on the size of the time quantum. At one extreme, if the time quantum is extremely large, the RR policy is the same as the FCFS policy. In contrast, if the time quantum is extremely small, say 1 millisecond, the RR approach can result in a large number of context switches. Assume, for example, that we have only one process of 10 time units. If the quantum is 12 time units, the process finishes in less than one time quantum with no overhead. If the quantum is 6 time units, however, the process requires 2 quanta, resulting in a context switch. If the time quantum is 1 time unit, then 9 context switches will occur, slowing the execution of the process accordingly. How a smaller time quantum increases context switches. Thus, we want the time quantum to be large with respect to the context switch time. If the context switch time is approximately 10% of the time quantum, then about 10% of the CPU time will be spent in context switching. In practice, most modern systems have time quanta ranging from 10 to 100 milliseconds. The time required for a context switch is typically less than 10 microseconds, thus the context switch time is a small fraction of the time quantum. Turnaround time also depends on the size of the time quantum, as we can see from the figure. How turnaround time varies with the time quantum. The average turnaround time of a set of processes does not necessarily improve as the time quantum size increases. In general, the average turnaround time can be improved if most processes finish their next CPU burst in a single time quantum. For example, given 3 processes of 10 time units each and a quantum of 1 time unit, the average turnaround time is 29. If the time quantum is 10, however, the average turnaround time drops to 20. If context switch time is added in, the average turnaround time increases even more for a smaller time quantum since more context switches are required. Although the time quantum should be large compared with the context switch time, it should not be too large. As we pointed out earlier, if the time quantum is too large, RR scheduling degenerates to an FCFS policy. A rule of thumb is that 80% of the CPU bursts should be shorter than the time quantum. Multi-level queue scheduling. A multi-level queue scheduling algorithm partitions the ready queue into several separate queues. See the diagram below. The processes are permanently assigned to one queue generally based on some property of the process such as memory size, process priority, or process type. Each queue has its own scheduling algorithm. For example, separate queues might be used for foreground and background processes. The foreground queue might be scheduled by an RR algorithm, while the background queue is scheduled by an FCFS algorithm. In addition, there must be scheduling among the queues, which is commonly implemented as fixed priority preemptive scheduling. For example, the foreground queue may have absolute priority over the background queue. Let's look at an example of a multi-level queue scheduling algorithm with 5 queues listed below in order of priority. 1. System processes. 2. Interactive processes. 3. Interactive editing processes. 4. Batch processes. 5. Student processes. Each queue has absolute priority over lower priority queues. No process in the batch queue, for example, could run unless the queues for system processes, interactive processes, and interactive editing processes were all empty. If an interactive editing process entered the ready queue while a batch process was running, the batch process would be preempted. Another possibility is to time slice among the queues. Here, each queue gets a certain portion of the CPU time which it can then schedule among its various processes. For instance, in the foreground-background queue example, the foreground queue can be given 80% of the CPU time for RR scheduling amongst its processes, while the background queue receives 20% of the CPU to give its processes on an FCFS basis. Multi-level feedback queue scheduling. Normally, when the multi-level queue scheduling algorithm is used, processes are permanently assigned to a queue when they enter the system. If there are separate queues for foreground and background processes, for example, processes do not move from one queue to the other since processes do not change their foreground or background nature. This setup has the advantage of low scheduling overhead, but it is inflexible. The multi-level feedback queue scheduling algorithm, in contrast, allows a process to move between queues. The idea is to separate processes according to the characteristics of their CPU bursts. If a process uses too much CPU time, it will be moved to a lower priority queue. This scheme leaves input-output bound and interactive processes in the higher priority queues. In addition, a process that waits too long in a lower priority queue may be moved to a higher priority queue. This form of aging prevents starvation. For example, consider a multi-level feedback queue scheduler with 3 queues numbered from 0 to 2, as shown in the figure. Multi-level feedback queues. The scheduler first executes all processes in queue 0. Only when queue 0 is empty will it execute processes in queue 1. Similarly, processes in queue 2 will be executed only if queue 0 and 1 are empty. A process that arrives for queue 1 will preempt a process in queue 2. A process in queue 1 will in turn be preempted by a process arriving from queue 0. A process entering the ready queue is put in queue 0. A process in queue 0 is given a time quantum of 8 milliseconds. If it does not finish within this time, it is moved to the tail of queue 1. If queue 0 is empty, the process at the head of queue 1 is given a quantum of 16 milliseconds. If it does not complete, it is preempted and is put into queue 2. Processes in queue 2 are run on an FCFS basis, but are run only when queues 0 and 1 are empty. This scheduling algorithm gives highest priority to any process with a CPU burst of 8 milliseconds or less. Such a process will quickly get the CPU, finish its CPU burst, and go off to its next input-output burst. Processes that need more than 8 but less than 24 milliseconds are also served quickly, although with lower priority than shorter processes. Long processes automatically sync to Q2 and are served in FCFS order with any CPU cycles left over from queues 0 and 1. In general, a multi-level feedback queue scheduler is defined by the following parameters: the number of queues, the scheduling algorithm for each queue, the method used to determine when to upgrade a process to a higher priority queue, the method used to determine when to demote a process to a lower priority queue, the method used to determine which queue a process will enter when that process needs service. The definition of a multi-level feedback queue scheduler makes it the most general CPU scheduling algorithm. It can be configured to match a specific system under design. Unfortunately, it is also the most complex algorithm, since defining the best scheduler requires some means by which to select values for all the parameters. Scheduling criteria. Different CPU scheduling algorithms have different properties, and the choice of a particular algorithm may favor one class of processes over another. In choosing which algorithm to use in a particular situation, we must consider the properties of the various algorithms. Many criteria have been suggested for comparing CPU scheduling algorithms. Which characteristics are used for comparison can make a substantial difference in which algorithm is judged to be best. The criteria include the following: CPU utilization. We want to keep the CPU as busy as possible. Conceptually, CPU utilization can range from 0 to 100%. In a real system, it should range from 40% for a lightly loaded system to 90% for a heavily loaded system. Throughput. If the CPU is busy executing processes, then work is being done. One measure of work is the number of processes that are completed per time unit, called throughput. For long processes, this rate may be 1 process per hour. For short transactions, it may be 10 processes per second. Turnaround time. From the point of view of a particular process, the important criterion is how long it takes to execute that process. The interval from the time of submission of a process to the time of completion is the turnaround time. Turnaround time is the sum of the periods spent waiting to get into memory, waiting in the ready queue, executing on the CPU, and doing input-output. Waiting time. The CPU scheduling algorithm does not affect the amount of time during which a process executes or does input-output. It affects only the amount of time that a process spends waiting in the ready queue. Waiting time is the sum of the periods spent waiting in the ready queue. Response time. In an interactive system, turnaround time may not be the best criterion. Often, a process can produce some output fairly early and can continue computing new results while previous results are being output to the user. Thus, another measure is the time from the submission of a request until the first response is produced. This measure, called response time, is the time it takes to start responding, not the time it takes to output the response. The turnaround time is generally limited by the speed of the output device. It is desirable to maximize CPU utilization and throughput and to minimize turnaround time, waiting time, and response time. In most cases, we optimize the average measure. However, under some circumstances, we prefer to optimize the minimum or maximum values rather than the average. For example, to guarantee that all users get good service, we may want to minimize the maximum response time. Investigators have suggested that for interactive systems such as desktop systems, it is more important to minimize the variance in the response time than to minimize the average response time. A system with reasonable and predictable response time may be considered more desirable than a system that is faster on the average but is highly variable. However, little work has been done on CPU scheduling algorithms that minimize variance. An accurate illustration should involve many processes, each a sequence of several hundred CPU bursts and input-output bursts. For simplicity, though, we consider only one CPU burst in milliseconds per process in our examples. Our measure of comparison is the average waiting time. Semaphores. In this section, we examine a more robust tool that can behave similarly to a mutex lock but can also provide more sophisticated ways for processes to synchronize their activities. A semaphore S is an integer variable that, apart from initialization, is accessed only through two standard atomic operations, wait function and signal function. The wait operation was originally termed P from the Dutch proberen, to test. Signal function was originally called V from verhogen, to increment. The definition of wait function is as follows. All modifications to the integer value of the semaphore in the wait function and signal function operations must be executed indivisibly. That is, when one process modifies the semaphore value, no other process can simultaneously modify that same semaphore value. In addition, in the case of wait S, the testing of the integer value of S smaller than equal to 0, as well as its possible modifications S minus must be executed without interruption. First, let's see how. Semaphores can be used, semaphore usage, semaphore implementation, deadlocks and starvation, priority inversion. Semaphore usage. Operating systems often distinguish between counting and binary semaphores. The value of a counting semaphore can range over an unrestricted domain. The value of a binary semaphore can range only between 0 and 1. Thus, binary semaphores behave similarly to mutex locks. In fact, on systems that do not provide mutex locks, binary semaphores can be used instead for providing mutual exclusion. Counting semaphores can be used to control access to a given resource consisting of a finite number of instances. The semaphore is initialized to the number of resources available. Each process that wishes to use a resource performs a wait function operation on the semaphore, thereby decrementing the count. When a process releases a resource, it performs a signal function operation, incrementing the count. When the count for the semaphore goes to 0, all resources are being used. After that, processes that wish to use a resource will block until the count becomes greater than 0. We can also use semaphores to solve various synchronization problems. For example, consider two concurrently running processes, P1 with a statement S1 and P2 with a statement S2. Suppose we require that S2 be executed only after S1 has completed. We can implement this scheme readily by letting P1 and P2 share a common semaphore sync initialized to 0. In process P1, we insert the statements S1, signal, sync. In process P2, we insert the statements wait, sync, S2. Because sync is initialized to 0, P2 will execute S2 only after P1 has invoked signal sync, which is after statement S1 has been executed. Semaphore implementation. Mutex locks suffers from busy waiting. The definitions of the wait function and signal function semaphore operations just described present the same problem. To overcome the need for busy waiting, we can modify the definition of the wait function and signal function operations as follows. When a process executes the wait function operation and finds that the semaphore value is not positive, it must wait. However, rather than engaging in busy waiting, the process can block itself. The block operation places a process into a waiting queue associated with the semaphore, and the state of the process is switched to the waiting state. Then control is transferred to the CPU scheduler, which selects another process to execute. A process that is blocked, waiting on a semaphore S, should be restarted when some other process executes a signal function operation. The process is restarted by a wake-up function operation, which changes the process from the waiting state to the ready state. The process is then placed in the ready queue. The CPU may or may not be switched from the running process to the newly ready process, depending on the CPU scheduling algorithm. To implement semaphores under this definition, we defined a semaphore as follows. Each semaphore has an integer value and a list of processes list. When a process must wait on a semaphore, it is added to the list of processes. Now, the wait function semaphore operation can be defined as wait open brackets semaphore asterisk s, shown in program below. A signal function operation removes one process from the list of waiting processes and awakens that process, and the signal function semaphore operation can be defined as. The block function operation suspends the process that invokes it. The wake-up P operation resumes the execution of a blocked process P. These two operations are provided by the operating system as basic system calls. Note that in this implementation, semaphore values may be negative, whereas semaphore values are never negative under the classical definition of semaphores with busy waiting. If a semaphore value is negative, its magnitude is the number of processes waiting on that semaphore. This fact results from the switching the order of the decrement and the test in the implementation of the wait function operation. The list of waiting processes can be easily implemented by a link field in each process control block PCB. Each semaphore contains an integer value and a pointer to a list of PCBs. One way to add and remove processes from the list so as to ensure bounded waiting is to use a FIFO queue, where the semaphore contains both head and tail pointers to the queue. In general, however, the list can use any queuing strategy. Correct usage of semaphores does not depend on a particular queuing strategy for the semaphore list. It is critical that semaphore operations be executed atomically. We must guarantee that no two processes can execute wait function and signal function operations on the same semaphore at the same time. This is a critical section problem, and in a single processor environment, we can solve it by simply inhibiting interrupts during the time the wait function and signal function operations are executing. This scheme works in a single processor environment because once interrupts are inhibited, instructions from different processes cannot be interleaved. Only the currently running process executes until interrupts are re-enabled and the scheduler can regain control. In a multiprocessor environment, interrupts must be disabled on every processor. Otherwise, instructions from different processes running on different processes may be interleaved in some arbitrary way. Disabling interrupts on every processor can be a difficult task and furthermore can seriously diminish performance. Therefore, SMP systems must provide alternative locking techniques such as compare and swap function or spin locks to ensure that wait function and signal function are performed atomically. It is important to admit that we have not completely eliminated busy waiting with this definition of the wait function and signal function operations. Rather, we have moved busy waiting from the entry section to the critical sections of application programs. Thus, the critical section is almost never occupied and busy waiting occurs rarely and then for only a short time. An entirely different situation exists with application programs whose critical sections may be long, minutes or even hours, or may almost always be occupied. In such cases, busy waiting is extremely inefficient. Deadlocks and starvation. The implementation of a semaphore with a waiting queue may result in a situation where two or more processes are waiting indefinitely for an event that can be caused only by one of the waiting processes. The event in question is the execution of a signal function operation. When such a state is reached, these processes are said to be deadlocked. To illustrate this, consider a system consisting of two processes, P0 and P1, each accessing two semaphores, S and Q, set to the value of 1. P0, wait S, P1, wait Q. P0, wait Q, P1, wait S, and so on, and then P0, signal S, P1, signal Q, P0, signal Q, P1, signal S. Suppose that P0 executes wait S function and then P1 executes wait Q function. When P0 executes wait Q function, it must wait until P1 executes signal Q function. Similarly, when P1 executes wait S function, it must wait until P0 executes signal S function. Since these signal function operations cannot be executed, P0 and P1 are deadlocked. We say that a set of processes is in a deadlocked state when every process in the set is waiting for an event that can be caused only by another process in the set. The events with which we are mainly concerned here are resource acquisition and release. Other types of events may result in deadlocks. Another problem related to deadlocks is indefinite blocking or starvation, a situation in which processes wait indefinitely within the semaphore. Indefinite blocking may occur if we remove processes from the list associated with a semaphore in LIFO, last in, first out order. Priority inversion. A scheduling challenge arises when a higher priority process needs to read or modify kernel data that are currently being accessed by a lower priority process or a chain of lower priority processes. Since kernel data are typically protected with a lock, the higher priority process will have to wait for a lower priority one to finish with a resource. The situation becomes more complicated if the lower priority process is preempted in favor of another process with a higher priority. As an example, assume we have three processes, L, M, and H, whose priorities follow the order L is lesser than M is lesser than H. Assume that process H requires resource R, which is currently being accessed by process L. Ordinarily, process H would wait for L to finish using resource R. However, now suppose that process M becomes runnable, thereby preempting process L. Indirectly, a process with a lower priority, process M, has affected how long process H must wait for L to relinquish resource R. This problem is known as priority inversion. It occurs only in systems with more than two priorities, so one solution is to have only two priorities. That is insufficient for most general-purpose operating systems, however. Typically, these systems solve the problem by implementing a priority inheritance protocol. According to this protocol, all processes that are accessing resources needed by a higher priority process inherit the higher priority until they are finished with the resources in question. When they are finished, their priorities revert to their original values. In the example above, a priority inheritance protocol would allow process L to temporarily inherit the priority of process H, thereby preventing process M from preempting its execution. When process L had finished using resource R, it would relinquish its inherited priority from H and assume its original priority because resource R would now be available. Process H, not M, would run next. Symmetric versus asymmetric multiprocessing. The multiple processor systems in use today are of two types. Some systems use asymmetric multiprocessing, in which each processor is assigned a specific task. A boss processor controls the system. The other processors either look to the boss for instruction or have predefined tasks. This scheme defines a boss-worker relationship. The boss processor schedules and allocates work to the worker processors. The most common systems use symmetric multiprocessing (SMP), in which each processor performs all tasks within the operating system. SMP means that all processors are peers. No boss-worker relationship exists between processors. Below diagram illustrates a typical symmetric multiprocessing architecture. Notice that each processor has its own set of registers as well as a private or local cache. However, all processors share physical memory. An example of an SMP system is AIX, a commercial version of Unix designed by IBM. An AIX system can be configured to employ dozens of processors. The benefit of this model is that many processes can run simultaneously. N processes can run if there are N CPUs without causing performance to deteriorate significantly. However, we must carefully control input-output to ensure that the data reach the appropriate processor. Also, since the CPUs are separate, one may be sitting idle while another is overloaded, resulting in inefficiencies. These inefficiencies can be avoided if the processors share certain data structures. A multiprocessor system of this form will allow processors and resources, such as memory, to be shared dynamically among the various processors and can lower the variance among the processors. The difference between symmetric and asymmetric multiprocessing may result from either hardware or software. Special hardware can differentiate the multiple processors, or the software can be written to allow only one boss and multiple workers. For instance, Sun Microsystems operating system Sun OS version 4 provided asymmetric multiprocessing, whereas version 5, Solaris, is symmetric on the same hardware. Multiprocessing adds CPUs to increase computing power. If the CPU has an integrated memory controller, then adding CPUs can also increase the amount of memory addressable in the system. Either way, multiprocessing can cause a system to change its memory access model from Uniform Memory Access (UMA) to Non-Uniform Memory Access (NUMA). UMA is defined as the situation in which access to any RAM from any CPU takes the same amount of time. With NUMA, some parts of memory may take longer to access than other parts, creating a performance penalty. Operating systems can minimize the NUMA penalty through resource management. A recent trend in CPU design is to include multiple computing cores on a single chip. Such multiprocessing systems are termed multi-core. They can be more efficient than multiple chips with single cores because on-chip communication is faster than between-chip communication. In addition, one chip with multiple cores uses significantly less power than multiple single-core chips. Synchronization hardware. There are a number of solutions to critical section problem. They are characterized based on tools. Simple tools: Peterson locks, synchronization hardware, mutex tools, robust tools, semaphores. Here we discuss only few as per the syllabus. Synchronization hardware. In the following discussions, we explore several more solutions to the critical section problem using techniques ranging from hardware to software-based APIs available to both kernel developers and application programmers. All these solutions are based on the premise of locking, that is, protecting critical regions through the use of locks. As we shall see, The designs of such locks can be quite sophisticated. Hardware features can make any programming task easier and improve system efficiency. The critical section problem could be solved simply in a single processor environment if we could prevent interrupts from occurring while a shared variable was being modified. In this way, we could be sure that the current sequence of instructions would be allowed to execute in order without preemption. No other instructions would be run, so no unexpected modifications could be made to the shared variable. This is often the approach taken by non-preemptive kernels. The definition of the test and set function instruction. The important characteristic of this instruction is that it is executed atomically. Thus, if two test and set function instructions are executed simultaneously, each on a different CPU, they will be executed sequentially in some arbitrary order. If the machine supports the test and set function instruction, then we can implement mutual exclusion by declaring a Boolean variable lock, initialized to false. Mutual exclusion implementation with test and set function, shown in program below. Unfortunately, this solution is not as feasible in a multiprocessor environment. Disabling interrupts on a multiprocessor can be time-consuming since the message is passed to all the processors. This message passing delays entry into each critical section and system efficiency decreases. Also consider the effect on a system's clock if the clock is kept updated by interrupts. Many modern computer systems, therefore, provide special hardware instructions that allow us either to test and modify the content of a word or to swap the contents of two words atomically, that is, as one uninterruptible unit. The definition of the compare and swap function instruction, shown in program below. The compare and swap function instruction, in contrast to the test and set function instruction, operates on three operands. The operand value is set to new value only if the expression *value equals exected is true. Regardless, compare and swap function always returns the original value of the variable value. Mutual exclusion implementation with compare and swap function, shown in program below. Like the test and set function instruction, compare and swap function is executed atomically. Mutual exclusion can be provided as follows. A global variable, lock, is declared and is initialized to 0. The first process that invokes compare and swap function will set lock to 1. It will then enter its critical section because the original value of lock was equal to the expected value of 0. Subsequent calls to compare and swap function will not succeed because lock now is not equal to the expected value of 0. When a process exits its critical section, it sets lock back to 0, which allows another process to enter its critical section. Although these algorithms satisfy the mutual exclusion requirement, they do not satisfy the bounded waiting requirement. In the below program, we present another algorithm using the test and set function instruction that satisfies all the critical section requirements. Bounded waiting mutual exclusion with test and set function. These data structures are initialized to false. To prove that the mutual exclusion requirement is met, we note that processes Pi can enter its critical section only if either waiting (i) double equals false or key double equals false. The value of key can become false only if the test and set function is executed. The first process to execute the test and set function will find key double equals false. All others must wait. The variable waiting I can become false only if another process leaves its critical section. Only one waiting I is set to false, maintaining the mutual exclusion requirement. To prove that the progress requirement is met, we note that the arguments presented for mutual exclusion also apply here, since a process exiting the critical section either sets lock to false or sets waiting j to false. Both allow a process that is waiting to enter its critical section to proceed. To prove that the bounded waiting requirement is met, we note that when a process leaves its critical section, it scans the array waiting in the cyclic ordering brackets I plus 1, I plus 2, and so on, n minus 1, 0, I minus 1, close brackets. It designates the first process in this ordering that is in the entry section, waiting j double equals true, as the next one to enter the critical section. Any process waiting to enter its critical section will thus do so within n minus 1 turns. System jobs. Several jobs are kept in main memory at the same time, and the CPU is multiplexed among them. These are called system jobs. Jobs, batch, are programs that run without user interaction. The number of job completions in a period of time is called throughput. There are various kinds of system jobs, long or short or interactive or batch jobs. Short jobs, a higher priority, perceived response time is thus better. Job accounting, keeping track of time and resources used by various jobs and users. To speed up processing, jobs with similar needs are batched together and run as a group. Multiple jobs are executed by the CPU by switching between them, but the switches occur so frequently. Data processing jobs are distributed among the processes accordingly to which one can perform each job most efficiently. The critical section problem. Consider a system consisting of n processes, that is, P0, P1, and so forth, Pn minus 1. Each process has a segment of code called a critical section in which the process may be changing common variables, updating a table, writing a file, and so on. When one process is executing in its critical section, no other process is allowed to execute in its critical section. That is, no two processes are executing in their critical sections at the same time. The critical section problem is to design a protocol that the processes can use to cooperate. Each process must request permission to enter its critical section. The section of code implementing this request is the entry section. The critical section may be followed by an exit section. The remaining code is the remainder section. The general structure of a typical process PI is shown in figure below. The entry section and exit section are enclosed in boxes to highlight these important segments of code. A solution to the critical section problem must satisfy the following three requirements. Mutual exclusion. If process PI is executing in its critical section, then no other processes can be executing in their critical sections. Progress. If no process is executing in its critical section and some processes wish to enter their critical sections, then only those processes that are not executing in their remainder sections can participate in deciding which will enter its critical section next, and this selection cannot be postponed indefinitely. Bounded waiting. There exists a bound or limit on the number of times that other processes are allowed to enter their critical sections after a process has made a request to enter its critical section and before that request is granted. We assume that each process is executing at a non-zero speed. However, we can make no assumption concerning the relative speed of the n processes. At a given point in time, many kernel mode processes may be active in the operating system. As a result, the code implementing an operating system, kernel code, is subject to several possible race conditions. Consider as an example a kernel data structure that maintains a list of all open files in the system. This list must be modified when a new file is opened or closed, adding the file to the list or removing it from the list. If two processes were to open files simultaneously, the separate updates to this list could result in a race condition. Other kernel data structures that are prone to possible race conditions include structures for maintaining memory allocation, for maintaining process lists, and for interrupt handling. It is up to kernel developers to ensure that the operating system is free from such race conditions. Two general approaches are used to handle critical sections in operating systems: preemptive kernels, non-preemptive kernels. A preemptive kernel allows a process to be preempted while it is running in kernel mode. A non-preemptive kernel does not allow a process running in kernel mode to be preempted. A kernel mode process will run until it exits kernel mode, blocks, or voluntarily yields control of the CPU. Obviously, a non-preemptive kernel is essentially free from race conditions on kernel data structures, as only one process is active in the kernel at a time. We cannot say the same about preemptive kernels, so they must be carefully designed to ensure that shared kernel data are free from race conditions. Preemptive kernels are especially difficult to design for SMP architectures, since in these environments it is possible for two kernel mode processes to run simultaneously on different processes. A preemptive kernel may be more responsive since there is less risk that a kernel mode process will run for an arbitrarily long period before relinquishing the processor to waiting processes. Furthermore, a preemptive kernel is more suitable for real-time programming, as it will allow a real-time process to preempt a process currently running in the kernel. Thread scheduling. On operating systems that support them, it is kernel-level threads, not processes, that are being scheduled by the operating system. User-level threads are managed by a thread library, and the kernel is unaware of them. To run a CPU, user-level threads must ultimately be mapped to an associated kernel-level thread, although this mapping may be indirect or may use a lightweight process, LWP. Contention scope. One distinction between user-level and kernel-level threads lies in how they are scheduled. On systems implementing the many-to-one and many-to-many models, the thread library schedules user-level threads to run on an available LWP. This scheme is known as Process Contention Scope, PCS, since competition for the CPU takes place among the threads belonging to the same process. When we say the thread library schedules user threads onto available LWPs, we do not mean that the threads are actually running on a CPU. That would require the operating system to schedule the kernel thread onto a physical CPU. To decide which kernel-level thread to schedule onto a CPU, the kernel uses System Contention Scope, SCS. Competition for the CPU with SCS scheduling takes place among all threads in the system. Systems using the one-to-one model such as Windows, Linux and Solaris schedule threads using only SCS. Typically, PCS is done according to priority. The scheduler selects the runnable thread with the highest priority to run. User-level thread priorities are set by the programmer and are not adjusted by the thread library, although some thread libraries may allow the programmer to change the priority of a thread. It is important to note that PCS will typically preempt the thread currently running in favor of a higher priority thread. However, there is no guarantee of time slicing among threads of equal priority. Pthread scheduling. Pthreads identifies the following contention scope values. Pthread scope process schedules threads using PCS scheduling. Pthread scope system schedules threads using SCS scheduling. On systems implementing the many-to-many model, The pthread scope process policy schedules user-level threads onto available LWPs. The number of LWPs is maintained by the thread library, perhaps using scheduler activations. The pthread scope system scheduling policy will create and bind an LWP for each user-level thread on many-to-many systems, effectively mapping threads using the one-to-one policy. The pthread IPC provides two functions for getting and setting the contention scope policy. pthread attr set scope open brackets pthread attr t asterisk attr int scope close brackets, pthread attr get scope open brackets pthread attr t asterisk attr int asterisk scope close brackets. The first parameter for both functions contains a pointer to the attribute set for the thread. The second parameter for the pthread attr setScope function is passed either the pthread scope system or the pthread scope process value, indicating how the contention scope is to be set. In the case of pthread attr getScope function, the second parameter contains a pointer to an int value that is set to the current value of the contention scope. If an error occurs, each of these functions returns a non-zero value. On some systems, only certain contention scope values are allowed. For example, Linux and Mac OS X systems allow only pthread scope system. Conclusion. In this chapter, we have covered the following in detail: processes, process concept, process scheduling and operation in processes, cooperating processes, interprocess communication, symmetric versus asymmetric multiprocessing, background process, CPU scheduling, process synchronization, deadlock.